Today we're going to continue section 10.2 on arithmetic sequences and series. But today what I want to focus on is finding missing information given information about an arithmetic sequence or series. So before I begin, I'd like to go ahead and review the two formulas that we have for the summation of arithmetic series. And the first one was our n over 2 times a sub 1 plus a sub n, where if we give the first term and the last term, we can find the sum if we know how many terms we had. The second formula was, again, the summation gave us as n divided by 2 times 2 a sub 1s plus the quantity of n minus 1 times d, where d was the common difference. And we're going to use either one of these, or possibly both of these equations, to solve a problem. So if we look at example 1, we're given s of 20, or the sum of the first 20 terms of a series, to be 500. And we know the 20th term to be 10. Can we find that d value? Well, if we first look at this, it kind of looks like we're solving and we're looking at this second equation because that's where our d is. So if I look, I know s of 20 would be 500. We know the number of terms is 20. So if I start filling that in, I have 500 equals 20 divided by 2 times 2. I'm not sure what a sub 1 is at this point. So we have 2 a sub 1s plus, we know the number of terms. The number of terms is 20 minus 1 times the common difference, which is what we're looking for. So if we look at that, we have now one equation, but we have two unknowns. That's our issue. So what can we do to find one of these unknowns? Well, a sub 1 is also in our original equation. So if we come back to this first equation, plug in what we know. We know the sum of the first 20 terms, when n is 20, to be 500. That's going to equal, we know the number of terms again is 20 divided by 2. We don't know a sub 1 at this point, but we know the 20th term to be 10. So can we go ahead and find our a sub 1? Sure we can, because we have one variable, one equation. Solving this equation, we have 500 equals 10 times a sub 1 plus 10. I can go ahead and divide both sides by 10 to get 50 equal a sub 1 plus 10. Subtracting 10, I end up with 40 equals my first term. Now that I know my first term, coming back over to this equation, I can replace my a sub 1 with 40 and go ahead and solve for d. So 20 divided by 2 gives me my 10. 2 times 40 gives me 80. 20 minus 1 is going to be 19. D. I'm going to go ahead and divide both sides by 10. So 50 is going to equal 80 plus 19d. Subtracting 80 from both sides, just solving a simple equation at this point, we get negative 30 equals 19d. And divided by 19, we end up with negative 30 19ths is going to equal our d value. And that allows us to find that common difference. So if I start at 40 and add negative 30 19ths, very ugly number, but doable, and if we add all those values together until we get to the 20th term, we'll end up with a sum of 500. In example 5, we're given the 15th term as 258. We're given a common difference of 3. Can we find a sub 1? So let's go ahead and see what we know, what we can find. So we know the 15th term, so 258, is going to equal n, which we know we have 15 terms, divided by 2, times a sub 1 plus a sub n. That's an issue. But remember, we're given our d value, and we're looking to find a sub 1. So if I go back to my other equation, well, in that equation, I know 258 is going to equal my 15 over 2 times 2 a sub 1s plus n. Well, I do know n. N is 15 minus 1, and I know that common difference, which is 3. Why did I put an extra 5 in there? We'll get rid of that. So 258 is going to equal 15 divided by 2, which is 7.5, or we can leave it as 15 halves, times 2 a sub 1s plus, here we have 14 times 3 will give us 42. Now I can go ahead and solve for a sub 1. So I really don't need this first equation at all. So 258, I'm going to go ahead and throw that in the calculator. I'm going to multiply it by 2 and then divide by 15. Is going to give me 34 and 4/10. Is going to equal 2 a sub 1s plus 42. Solving this equation, I can subtract 42 from both sides. Again, using the calculator, negative 7 and 6/10 equals 2 a sub 1s. Divide by 2, we know that a sub 1 is going to equal negative 7.6 divided by 2, which is going to be negative 3 and 8/10. And that allows us to find our a value, our first a value. Example 3 and 4, I want to take a minute to look at sigma notation and being able to build a sigma notation when given a specific lower boundary. Again, these are going to be arithmetic sequences and series, so we can use some of those formulas that we know from the past. So again, if you remember, the explicit formula for an arithmetic sequence and series is going to be given as a sub n equals a sub 1 plus the quantity of n minus 1 times d. So do I know any of this information? Well, I know my first term is 5. I know my last term is 45. I also know the common difference. So as I build my sigma, I know that I got to start at n equals 3. Well, what is my equation going to be? Well, I know that my nth term is going to be given by my first term, which in this case is 5, plus n minus 1. I want it in general terms of n. I know my common difference is going to be 4. So I multiply that by 4. So in general, my equation is 5 plus 4 times n minus 1. Written a little nicer. But I know when I plug in n equals 3, it's got to give me that first term. Well, if I plugged in 3 here, I'd have 4 times 2, which is 8, plus 5. That gives me 13, a little far off from 5. But if we notice, we're multiplying this 4 by n minus 1. And we're going to add 5 to it. That 5 is really what I want to get to. So if I zero this out, I'm going to be able to get my first term in my sigma notation. So in order to zero this out, that n minus 1, when I plug in 3, is really going to be an n minus 3. Because if I plug in 3, 3 minus 3 gives me 0. Multiply that by 4, I get 0. Adding to 5, I end up with 5 as being my first term. So my equation is going to be 5 plus 4 times n minus 3. I can clean that up just slightly to 4n minus 12 or 4n minus 7. Now, if we were to plug in our 3, 4 times 3 gives us 12 minus 7 gives us 5. As I increase, I plug in 4. 4 times 4 is 16, minus 7 gives me 9. So we see that this formula is going to work for us. One more, if we plug in 5, 5 times 4 is 20, minus 7 gives me 13. So I know that that is going to be my explicit form, 4n minus 7. The question is, how far do I go up? Well, I know that my last term is 45. So if I use this equation, 45 is going to equal 4n minus 7. That's going to allow me to figure out what number I have to plug in order to get that 45. So here I can go ahead and add 7. And I get 52 equals 4n. So n is going to equal 13. So I know now my segment notation, I go from 3 to 13 of 4n minus 7. And one last one, just to practice writing their segment notation. Here I'm going to give you n equals 6 and the series of 7 plus 2 plus a negative 3, so on and so forth to negative 18. Again, I'm going to go ahead and start by setting up my general equation, a sub n equals my explicit equation, my first term, which is 7, plus n minus 1 times my common difference. My common difference in this case is negative 5. As I set up my sigma, I know that my bottom or my lower bound is 6. And if I plug in 6 here, I've got to be able to get 7 out. So again, I've got to zero this part of my equation out. Well, how is that going to happen? Well, if I take n, which would be 6, and I subtract 6 from it, and multiply it by a negative 5, that'll zero that out from my first term, and I'll end up with 7. So I end up with n equals 6 as being my first term. So now I can go ahead and simplify this. I get 7 plus a negative 5n plus 30. Simplifying that, I end up with negative 5n plus 37. We can definitely go ahead and check this. If I plug in 6, negative 5 times 6 is negative 30 plus 37 gives me 7. If I plug in 7, negative 5 times 7 is negative 35, plus 37 gives me 2. So we see that that's going to be my explicit formula. And again, where do we end? Well, I know I've got to get negative 18 when I find my last value, when I plug in my upper bound. So I go ahead and solve this equation. I can subtract my 37, and I get a negative 55 equals a negative 5n. Divided by negative 5, I end up with 11 equals n. So my upper bound now is going to be 11. And that allows us to be able to take an arithmetic series and write the sigma notation given any n value or lower boundary.